Assalamu alaikum, dear students. So after the completion of the complex reaction, today I am going to explain you the next topic, that is autocatalysis. So autocatalysis is actually the process or phenomena in which one of our reaction product work as a catalyst for the acceleration of our subsequent reaction. In this case, the rate of the reaction slowly increases, but once we have some product formed and that product further accelerate the reaction, so we have a quite good increase in the rate after we are getting some product. And the plot between the rate of the reaction and time, we are getting a sigmoidal curve, and that sigmoidal curve actually reach a maximum value when once we have the reaction going toward completion. And if you plot a graph between the concentration of the reactant and product versus time, so initially the concentration of the reactant decreases very slowly because we don't have any product, and once we have that catalytic product produced, that product work further as a catalyst for the increase of the reaction rate. So we have a sudden drop in the reactant concentration after some time and a sudden increase in the concentration of the product, and we are getting a maximum once we have reaction going toward completion. So this I am going to explain you step by step, and this look like the rate law equation look like a second order mixed rate law equation as we have previously discussed and derived. So at the end we will get the same equation, and after that I'm going to explain you a few example of autocatalytic reaction. Today I'm going to explain you the topic autocatalysis. So what is autocatalysis? Autocatalysis is a phenomena in which one of the product of the reaction acts as a catalyst for the acceleration of the reaction, or this is the catalysis of a reaction by one of its product. Here the initial rate of the reaction increases slowly as the catalytic product is formed, will speed up the reaction steadily, and the curve between the rate and the time show a maxima at the completion of the reaction, and the curve is a sigmoidal curve. It's similar to sigma sign. You can see this curve here. This is the curve between the rate of reaction or the percent reaction, and on this x-axis we have the time of the reaction. In the beginning you can see here the rate increases very slowly, but once we have a catalytic product produced, it will speed up the reaction, and we have a linear or exponential increase in the rate of the reaction. And here we have a maxima where the reaction goes to completion. In the same way, if we plot a graph between the concentration of the species, that is reactant and product, and time of the reaction, so initially the concentration of reactant is the highest, and its concentration decreases slowly, but once we have a catalytic product produced, so the concentration of this reactant decreases very quickly. So you can see that a quick decrease in the concentration of reactant and a quick increase in the concentration of product, and at the completion of the reaction we have a maximum highest concentration of product. So this shows the completion of the reaction, and this is the zero concentration of reactant with the passage of time. This is a very general reaction in which the rate of the reaction accelerates as the reaction progresses. This reaction is a first order reaction which is catalyzed by the product B as reaction progresses. As B is formed, the rate of reaction will increase, and the first order plot will deviate from linearity with high slope. So if we have high slope, we have fast reaction, or the K value is higher. This was a general plot. We already derived this for the first order reaction, and this is between L and A in concentration of reactant at any time versus time. So this is the plot which has lower slope. This is the real plot for this kind of reaction. So here is a sudden increase in the slope, and this increase shows that the product accelerates the reaction. For the first order reaction, we should get this kind of plot, but in this case, once we have catalytic product produced, it increase speed of the reaction and we have highest slope. At any time t, the concentration of A consumed is equal to the concentration of product B formed, in which reactant A is going to product B. At time t is equal to 0, the initial concentration of A is maximum and the initial concentration of B is 0. After time t is equal to any time t, sum of reactant A is converted into product. So the amount of A consumed will be given by A naught minus A. So this is initial and this is at any time t. So this will give us the amount of A, reactant A consumed, and this show the amount of product B formed at any time t. So if the stoichiometry of the reaction is followed, we have the amount of A consumed will be equal to the amount of product B formed at any time t. Solving for the concentration of B, just taking this B on one side and transferring this to another side. So we solve for the concentration of B. Now putting the concentration of B in our first order equation first, equation number 1, and after rearranging, transferring this T to one side and the concentration to another side and rearranging, we got equation 3. This equation 3, if you closely look to this equation 3, this equation 3 is similar to one of our second order mixed rate law, in which we have the same denominator, although there was some change of sign, negative positive, but the denominator look like same, and this denominator is a combination of two factors, that is A and this another value of B. So this denominator can be solved by method of partial fraction in the same way. Taking this denominator and solving this by separating the fraction, so we got constant C1 and C2. This is equation X. Now taking the same right hand side and solving this, adding the term, taking LCM. So this we got equation Y. If you look at the equation X and Y, the right hand side of equation X is similar to the left hand side of equation Y. So comparing both, so we have this term will be equal to this term in the same way here. The denominator in both on both sides, they are equal, so they can be cancelled, and we got this equation 4, simplified equation 4 is equal to 1. The reactant A is consumed completely, then the concentration of A is equal to 0. Just putting this A is equal to 0 in equation 4, the equation 4 will become, this factor will become 0. This we will get this simplified form of equation 4. From this we can take out the value of C1. C1 is equal to 1 over A naught plus B naught. This is equal to C2, and how this become equal to C2? Because this equation is equal to this vector. If we have this vector is equal to 0, so this equation will be valid. In this equation, we are taking this A, concentration A common, is the concentration of A at any time during all the reaction cannot be equal to 0. So if this is not equal to 0, then the constant term should be equal to 0, because the product of both we should get a 0. And if we make this constant is equal to 0, or transferring this C to another side, so we have C2 is equal to C1. If you look closely, or if we remember, last time we got this C1 is equal to minus C2, but in this case we got positive sign. So the final equation will be not the same as we got in the second order mixed rate law. Now just putting the value of this you can see here that how this C1 is equal to C2 now putting the value of C1 and C2 in equation 3 after modifying. So equation 3 can be modified by putting the value of this separated friction term. We just took this minus dA common and we put the value of the separated friction, and the next step we have to put the value of this constant C1 and C2, and that is this value C1 is equal to C2 is equal to 1 over A0 plus B0. So this term is common in both in this and this, so we can take this after putting, we can take this common is this one, and this is inside. So just keep in mind this is the concentration of A, this is B, and this is A, but this term is the concentration of B is we put last time in the beginning of the reaction. You can see here. So this is the concentration of B. If we have time t is equal to 0, the initial concentration of A is represented by A0 and the initial concentration of B with B0. Similarly, the initial the concentration at any time t of A with A and of B with B. So this equation can be solved by integrating between these limits. Just applying the limits, initial limit and final limit. Similarly, the initial limit of B and final limit. We are using this general integration formula. We already used this before. If we have 1 over x dx, we are getting ln x. This is independent integration. We are getting constant c here, but here we have definite integration between limits. After applying the limits, so we got this final limit minus initial limit. Similarly, final limit minus initial limit is equal to kt. So rearranging the log term and this product term, applying the minus sign to these log terms, just reversing this, so the minus sign can be cancelled. So just rearranging, we got this final equation. This common term is transferred to another side, and we got this final equation. And this equation, the value of k is very, very important. So if we put the initial concentration of A0 and product B0, similarly the final concentration or the concentration at any time t of A and product B, so we can get the value of rate constant for a particular autocatalytic reaction. Example of autocatalytic reaction or autocatalysis. The simplest example is the hydrolysis of ester, in which acetic acid is formed, and this acetic acid work as a catalyst for the acceleration of the reaction. Similarly, the oxidation of oxalic acid. Oxalic acid can be oxidized in the presence of KMnO4 and sulfuric acid. So we are getting manganese sulfate, which work as a catalyst for the acceleration of subsequent reaction. Hope this